Okay, so for today's demo, I want to talk about a clustering technique that's specialized um, for graph data structures. So specifically, I'm gonna show how we can cluster a large graph. So just to get a sense of what type of graph we're talking about, I'm talking about graph networks. So yeah, so we're gonna, the idea of today's topic is to have a super large graph and, well, generate a super large graph, and then, and the specific algorithm that we use to generate this large graph is an algorithm particular to graph networks, and it's called a small world graph. So, small world graph. So yeah, so the idea is to generate a super large graph based on the small world graph random graph generator technique. So as the name says, essentially we're simulating a large graph, but we want the graph to be as close as a real network as possible, a real world network. So there's actually an algorithm for that called this small world graph, and essentially you can visualize it in two ways. One is sort of you first create sort of connections with nearest neighbor of each node, and then you can start sort of amplifying the diameter. So you would ideally disconnect, let's say that one of these randomly generated edges, and you would connect it somewhere further away. So that would sort of generate something like this type of graph. So that's the graph that we're going to be generating today. So after we generate this super large graph, by super large graph I mean exactly 1 billion edges. We're then going to perform a probabilistic data structure called MinHash for clustering said graph. So one of my favorite topics in the technical field, I guess, is probabilistic data structures. So actually, I wrote a library for different probabilistic data structures, and the one that's specific to clustering, that can be used as clustering, can be either MinHash or SimHash. But for this case, I'm going to use a modern variant of MinHash algorithm, and yeah, that's essentially a clustering sort of technique. Except this is an approximate clustering technique, which means that we're probably not going to have an exact solution, but it's going to be much more efficient than what it would run if you do an exhaustive clustering algorithm. So in the case of big data, approximation or approximate solutions are super useful because it's almost impossible to kind of do a full data scan or a full data pass many times, because I guess your data points can be, let's say, like for DNA in the billions. Also, the graph I'm showing is also within the billion data points, and ideally you don't want to do too many passes on the data. So part of my previous experience has to do with big data technologies. So that's why I chose to. So we're gonna. The idea is that this graph clustering technique is embarrassingly parallel. This means that it can be parallelized quite well. So that's why. So I'll introduce like the framework and all of that I'm going to use. So I guess the computational framework that we're going to use for this particular demo is called mapreduce framework, which means that, okay, we have essentially a cluster of nodes. In this case, we can have up to as many nodes as we want, as many compute nodes or hosts or machines. And so we have this in a cluster. They're networked together, these machines. So they can each pretty much talk to each other, so to speak. So the idea of MapReduce framework has to do with, okay, we have a super large problem. Let's say that we have a large problem right here. But this large problem is impossible to fit into one computer's memory. So the idea of this is to kind of partition the problem in such a way that you can take each of these smaller chunks and map them to a particular machine. So in this case, the clustering algorithm that I want to work, so it's a 1 billion edge graph cluster, and it's not necessarily going to fit into memory of one single machine. So and the whole graph is not going to fit into one single machine. So we're going to partition this large graph first, kind of, and then we're going to assign, let's say, some jobs. So for example, we would partition this into jobs. So job 1, job 2, job 3, job 4, and all the way to job n. So ideally, when you do MapReduce processing, the idea is that each of these jobs gets assigned to a node. So in this case, let's say that I want to cluster this. So the partition 1 would get assigned to this machine. Partition 2 would get assigned to this machine. Partition 3 to this machine, and so forth, so on and so forth. There are different scheduling algorithms of how you would like to schedule each portion of the problem. But in this case, if you just take a normal round-robin approach, it could be something like this. Then job 4, job 5, and job 6. So that's essentially the MapReduce framework that we're going to use. And in regards to the big data technology, or the cluster that we're going to use a Kubernetes cluster right here. And we're going to do a type of processing that is very similar to Spark, except we're not going to use Spark, so to speak. So the idea of Spark, which is a very famous big data processing technology, is essentially what we just did. So we first map the problem. We break the problem down into many pieces. We map them onto different workers, and they don't have to be mapped at the same time. So we'll look at this during the demo. But essentially, I guess what Spark does is it breaks down it maps the problem onto different workers, and then it does a reduce phase. So hence the name MapReduce. So during the reduction phase, we're going to gather the results of all the processing tasks that got submitted or executed, and then we're sort of going to try to gather all of it can be like very many tasks. So the idea here is that we're going to sort of group all of these results into just one single result. So this is called the reducing phase. Similarly, for node 2, we're going to group all of these nodes. Specifically, we're going to group by ID, and we're going to just have a one result per node, so to speak. So that's sort of the result phase. And the last phase for this is called a result. So we already talked about map. Reduce means just group everything into the same node. And the result is going to do the same reduce phase, except it's going to do it for every node. So ideally here, I didn't mention, but here our setup is we also have an external storage source. In this case, it's an external NFS mount. So I guess the idea would be to kind of group all of these together in the similar phase to what we did right here, but leaving us with one sort of Uber result or one macro result for the whole cluster. So once we perform this reduce again, where we're going to group by ID over all of these, we're just going to have one, let's say we call this the result. So the result for the big data problem would be right here, and That's pretty much MapReduce. So we already said, okay, we're going to cluster a 1 billion edge graph, and this is the computational framework that we're going to do it on. So for this, we chose Kubernetes cluster. This is essentially what Spark does under the hood. And it's important for this sort of theoretical walkthrough to talk a little bit about the a tool that I'm going to use for kind of it's called a pipelining tool. So usually whenever we execute these types of graphs, and let me just go ahead and do this in a new sort of drawing board. So usually whenever we execute these types of complex tasks, we need to execute them in such a way so these are not necessarily sequential tasks or fully parallel or fully sequential tasks. In this case, we're going to have more of a DAG, what's called a DAG, a directed acyclic graph. So in order to, let's say that the MapReduce, in this case, we're going to kind of map it onto a computational flow but let's just call it, so there are different terminologies, but certain technologies call it workflow. Other technologies call it pipeline, like for example, Kubeflow pipelines. Argo has Argo workflows. Airflow has Airflow task flows. And even like ETL, certain ETL engines have a similar concept of task flows. So what this means is essentially that we're going to create a DAG execution graph. So DAG, and let me tell you what a DAG is. So a DAG is something, just look for a good example. Maybe, here we go. Okay, so this is an execution flow, a DAG. So this is what this is actually another tool that we're going to use today. It's called Argo, and I'll talk about why we've chosen this solution. So as you can see right here, usually whenever we have more complex execution flows, we usually have something that's called a dependency graph. So for example, in this case, the line is very faint, but we have 3 lines right here, one line here, one line here, and one line here. That means that all of these 3 processes or jobs depend on this job to complete, because these jobs are going to use some result of this job in order to process their own, in order to execute their own process. So here, for example, we show that, okay, log trigger depends on log. Similarly, we have like a separate branch here that workflow depends, Argo workflow depends on workflow, and they all depend on ultimately the example with interval, right? So this is a very common, very common to have these complex sort of execution workflows. So today I've chosen to, I'm going to show like the program, the actual code, and then I'm going to show how we containerize it. We create a pod, how we would run it into a job and all of this. And on top of that, I also want to show sort of, so we installed Argo on our Kubernetes cluster in order to create a MapReduce DAG, which just basically means, okay, we have 3 simple stages. We have a map stage. Let's see right here. So that's introduction to Argo and the workflows, and directed acyclic graph. That's just a dependency graph. But for the case of MapReduce, so for example, we're going to have first a mapping phase where each job let's call this mapping. Each job it's gonna execute, and we actually have a dependency here. So we first must complete all of the mapping phase before we start with a reduce phase, because the reduce phase is gonna take all of these sort of partial results and combine them, so to speak, into like larger results, one per node. And then lastly, I guess this is a very similar sort of DAG. But lastly, we're going to have the result phase, which is also dependent on the reduce phase. So the result phase right here is going to pretty much combine all of these. It first needs to wait for all of these to complete before it can combine pretty much the final solution. So let me just. So yeah, the technology we chose for this is Argo, and here's our webpage right here, Argo workflows. And this is native to Kubernetes, so that you can sort of create these complex direct acyclic graphs. So here it shows kind of like complex workflows. So yeah, I think that that's pretty much sort of the theoretical aspect of and the layout of what we're going to be doing today. So let's just go right into like let's just go right into it. So the first let's talk about like the actual code that's going to execute this. Let's just talk about the actual code. So I'm currently interested a little bit in the Rust program. So this whole code, I've written it from scratch, and it's purely Rust. So you can see right here, it's pure Rust. This Python code right here is used mainly for just to kind of show some dashboards. It's a small Python script. But essentially, let me just show kind of like the structure of the code. So first, I mentioned that we have we chose a. So we have our entry point, so to speak. So we have our main sort of our main function that's going to take certain arguments, and then we essentially have three different execution modes. So we have map mode, reduce mode, or result mode, and this is where we'll see how to execute this further down the line. So essentially, these are arguments that we can pass depending on what stage we're currently at. And also, so the code particular to each of those phases, so to speak, is right here. So map, reduce, and result phase. We call all of these from the main function, and so I've chosen a specific algorithm. The main author is Ping Li. He's a really he's really good at I guess one of the best guys I've seen in regards to like approximate solutions in general. So he's one of the best for the MinHash algorithm and all of its variants. And in this case, I chose to implement one of his papers, which is called circulant one permutation hashing, and I'll show it right here. So this is Ping Li and Xiaoyong Li in this case. But I've been following like Ping Li's work for a while, and he's pretty much MinHash king, so to speak. But yeah, this is the all this paper's implementation down to Rust code is right here. So essentially, I'm creating a MinHash table. You can also think of it as a COP hash table, but yeah, I'm not going to show the further details of the code, but maybe just the struct right here. So yeah, so it's optimized. So in essence here, notice how we have U32-bit, so 32-bit, a 32-bit hash map here for the index. So that means that this particular hash table can have up to around 4 billion entries. And I guess this is already optimized. So yeah. So okay. So that's the algorithm that we're going to be using for clustering. Here's the paper. It's I really enjoyed reading it and also implementing the code down to the Rust language and optimizing it as well. But yeah, this is the logic that we're going to use. So that's the code. Notice here that we have actually a Docker. We have a Docker file right here. So we're actually Dockerizing this code right here. And I'm actually going to show you so this is the image that got created. So notice how, I guess the only thing I want to show about this image, we'll actually see it further. Yeah, we'll reference this image within the pods, but notice the size of the image. So it's a small footprint image, 4 megabytes. And yeah, I guess yeah, I also optimized this image to be as small as possible, in such a way that the code is optimized, the image is optimized, and also ideally, I guess the all of the stack that you can optimize. It's always a good idea. So yeah, this is the image that we're going to be using today. And actually, here for example, I usually have this structure for all my projects or projects that are particular to Kubernetes. So for example, here we have all the Kubernetes scripts. So kube, let's just say we're going to have the declarative YAMLs. So in this case, and I'll walk you through this so that you can get a sense of what's going on. So if you're familiar with Kubernetes, you already know what this is. You're familiar with YAMLs and all of this. So in this case, we're just going to execute a job. And the image is the image that we just showed right now. We already showed what's inside of the image. And we also showed, okay, whenever we execute this argument, essentially, so this image already contains the compiled code. And we can have like different arguments within our code. So we can have, I just chose to, for example, the stage, S means stage. I think Spark uses the same nomenclature. But essentially, this is the mapping stage. We want to generate with a small world graph 1,000 edges, and then and then we're actually going to cluster those 1,000 edges within this same code. So that means that this block of code is embarrassingly parallel. That means that it can run independently from other code. And we're going to write the output so we're generating and then we're clustering the code. I didn't show the code for that, but it's essentially running the circulant, the MinHash modern variant, so to speak, which is gonna generate, which is gonna put all of the edges that are similar. It's gonna bucket them into, it's gonna cluster them, so to speak, put them into the same bucket, and we're gonna write that result to our local here it is, to our local host on this mount point right here. And that's it. That's the mapping phase. Now let's go ahead and look at the reduce phase. The reduce phase here, unfortunately for me, I was looking for a resource, a Kubernetes resource that was named something like a daemon job, something that runs once, a job that runs on each node. But I did not find such a, there is actually not such a resource. So I essentially had to hand code this. So I have 3 nodes, three compute nodes, and then I'm going to be running one reduce job on each of them, on each of the nodes. So let me talk about a little bit about this. So here we're going to use the same code, except this stage is going to be reduce. We're going to take our partial results, and then we're going to write them to some external source. So here are the mounts for this particular pod. Notice here that we have our partial results that we did during the mapping phase, and then for the result, we're going to go ahead and send that over to some external data source. In this case, we have an external NFS machine with this directory that's going to be receiving these results. So they're all going to be sending the results to taking the results from their local volume and then sending them to that same external volume. And you might guess that the last phase is going to be the result. And here we're actually just going to take the, we're going to aggregate all of the reduce files, whatever has arrived here, and we're just going to, I guess, so the stage is result, and then we're just going to aggregate all of those. We're going to group by key, so to speak, so that we have now a super large clustered graph. And the result, we're going to just write it to the same location. So that's the three pods that we created for this, and let me just, I want to sort of demonstrate how Argo workflows work. So here, for example, we can, after we install Argo workflow, we can declare this custom resource, and we can create, like, this is the DAG, direct acyclic graph, and essentially here you can sort of give the different steps that you want your DAG to take. So recall that the DAG is visually something like Argo workflow DAG. So yeah, it's just, so this is the visual portion, and then of the DAG. This is how you would declare it. So every component right here maps to it's sort of like, you can think of it as the metadata, and the actual execution, so to speak, is down here. So notice how here, so there are different there are different execution modes you can have down here. So for example, you can run a like a shell script, or I don't know, very many execution modes. In this case, since we're on Kubernetes, I chose, so you can pretty much just copy and paste your after you define all the structure of the DAG, you start defining sort of like the specific. So for example here, the reduce 0 phase is right here, and here you would specify, okay, the template reduce 0, what maybe it has a dependency. So here this reduce depends on the map, sort of yeah, the dependency for this is the map phase. You need this job to complete before you can start the rest. So that's essentially it. In this case, we can literally just, so for example, copy and paste. Let me just show one example here. The map. So even like if I Control C all of this, and then I can, let's see if it. Oh, maybe it's not, but it's essentially a copy paste of this. So just let me show how you could create these. So something like that. So notice how it's pretty much the same. Maybe different name because we're going to execute different workflows, but yeah, just I guess you get the point. So for the reduce one, we also did all the reduce, and we kind of declare them here, and then finally we're going to have the result from this workflow. And this is essentially an Argo workflow, a defined Argo workflow. Okay, so I think, yeah, we've sort of talked about the intuition of how this works on Kubernetes. Now let me go ahead and walk you through the README. So I'll just do that right here, actually. You may notice that I just updated this a little while ago, just before this demo. So these are some of the things to consider, maybe, whenever you're going to install it. So first, as a prerequisite, is you need to have two things, or, well, you need to at least have a Kubernetes cluster. So now let's just go ahead and, so this is my laptop right here, and I'll just go ahead and SSH to my Kubernetes master. Kubernetes master, remember, okay, so here we talked about having a Kubernetes master and 3 worker nodes, and then we have an external NFS node right here. Let me just show you that setup. So kubectl get nodes, and here we have, this is our Kubernetes master and 3 workers. And I guess here I have an NFS server on a machine that's 100 on. So just to put a name on them, worker 1, worker master is 0, 1, 2, 3, and this is 5. Worker, let's just call it machine 5. So yeah, so let's just SSH to worker 5. I mean SSH L10U at 172.10.4.105. So this machine right here is going to have our NFS an NFS server. That we've mounted onto this CD SRE. So all of our Kubernetes data, or the FS tab that we configured for this, so that we can write, we can access this NFS directory. So it's right here. Anyhow, we'll just get back to it. Okay, so that said, we said we have 3. This is our setup. Now let's go ahead and start executing stuff. So, okay, let me just. So we have a Kubernetes cluster. We have that external external storage. Now, so I just for convenience, I'm using a cluster shell utility. So what this does is that we can we don't need to navigate between one terminal and many terminals. So let's say that I want to run this date command. I could essentially just run like the clutch and then run date on all of these different machines. So it's very simple to configure. All you need is this. This is a way to install it on a Ubuntu. This is Ubuntu 22 right here. And notice how, so I just barely installed the latest Kubernetes version. So this is latest version installed today. But let's continue with clutch. So let's say that I don't want to. So here we configured all of the machines that we're going to be working with. I kind of just took these and grouped them because they're Kubernetes workers, and then something else like the external NFS. So let's say that I want to just execute something on only Kubernetes workers, or whatever grouping you may have. So you can do something like this. So let's do the date command on these 3, and there we have it. So that's it. And we'll get to why we install this later on. Go ahead and install Argo. So kget namespaces. Notice that this is just like a brand new Kubernetes cluster. There's nothing in it. Kget all. Well, there's only like the network, sort of the CNI, but nothing else. Just the core Kubernetes cluster. So let's go ahead and create. So these are the steps mentioned pretty much in the quick start of Argo. So we'll just walk through them right here because there is a thing. Yeah, let's just do it. So this is a resource that Argo publishes. So here, for example, we're applying all the resources and the custom resources, the roles, maybe some service accounts right here, and so it also has some deployments, and yeah, that's all the resources that Argo provides. Optionally, you can also install the Argo client, which I think we can. Okay, yeah, let's go ahead and install it, but it's optional. We really don't need it. and you'll see why further down in the demo. And this is also part of the official documentation. So Argo, maybe like a quick start. So it's, yeah, so notice how here we're following pretty much the same steps. Well, similar steps, I guess, yeah. We're working on the, okay, never mind. So let's unzip this downloaded client binary. Let's give it executable permissions. Go ahead and move it to the Argo. And this, so, okay, let's test that our version got installed, our Argo, and there it is. So we have this, the latest version as of today. So here, optionally, you can submit a you can submit a job. But for now, we're gonna go ahead and skip this step. Maybe we can, let's just look at the workflow, just for heck's sake. So this is a really small workflow, similar to the one we showed earlier. Notice how it has some logic in there, and it has an image, and it runs a command. And yeah, that's pretty much it. For now, let's just go ahead and, so one thing I noticed, in our case, we want to execute Argo, not Argo, but Kubernetes jobs. Remember that we showed a YAML files that had jobs in them. So here, whenever I ask Kubernetes, hey, can my service account Argo create jobs? And the answer is no, we don't have these permissions. So we have to give it the permissions that we require. To be able to create jobs and these, yeah, for our particular use case. So first, let's go ahead and switch the context to the Argo namespace, just so it's easier to kind of configure this. Next, let's go ahead and look at all the role-based access controls, and so just to see what we need to modify. We're going to modify actually two, one role and then one cluster role. So first, let's start with a role. We're just going to go ahead and extract it. So notice how this is the Argo role that we found up here. Then we're writing it to a local YAML that we can edit and then reconcile back to the cluster, or update the sort of the RBAC, role-based access controls. Okay. And we also need this cluster role. So now that we have these here locally, this is actually part of like an old demo. It uses another scheduler, but here in this case, we're only gonna kind of use this part. So here, vi cluster role, and in this case, I guess for simplicity, I'm just gonna give full permissions to the Argo service account. For the role, sorry, for the role, yeah. Okay, so here, for example, API groups. So let's go ahead and do that. Resources, verbs. Okay, so this is repeat. Okay, so we have two API groups. Okay, so for each API group, let's just give it full access. Okay, and here as well. And here, let me see if I can reconcile this. So when you do Did not find expected key, YAML 22. Okay, let's like this. Yeah, okay. Batch. Why do we have batch here? So let's try this. I think I know what happened. Here, let's just do that. What is it, line? I think we can even do something simpler. So all API groups, and just give it everything. So I'm not sure if we need to specify the Argo proj. Let's just try this, just to be safer. Or let's expecting this. Oh, okay, so it's added the rules. Now let's go ahead and try the let's try the role one. So we already have the role here. Yep. Okay, so let's edit that role. And let me just make sure I do the correct thing right here. Okay. API groups, yeah, that one. And let's just say you can do everything. Oh. And just to be safe, I'll just do this one as well. Anyhow, okay. Now let's reconcile this guy as well. Roles. Okay. Okay, so it seems like it's added these roles as well. Let's go ahead and test. So remember we first just did this command, and it said no, you can't run Argo jobs. Now Kubernetes jobs. Now let's try this again. And okay, so now that we've updated the RBAC to the service account, we can now run jobs. That's very important because all our resources are based on pretty much on jobs. So so for example here, recall we talked about, okay, all our resources are mostly of kind job. So for example, let's just test another thing. Maybe can I create pods? Yes, it's because we gave it the full access. So can I create namespaces? Yes, etc. Okay. So moving forward, I think we're ready to we're ready to run a quick MapReduce job test, so to speak. So the way I've structured the project is each node is node, I guess the worker nodes 101 to 103 is going to have a local directory called mount data, and this is where it's gonna store the partial results of the mapping phase or stage, sorry. And then for the external storage, so actually this is better. For the external storage, we're gonna have this directory that's gonna store the result and the reduce files that we're gonna be. So whenever we run the reduce step, we're gonna send whatever reduced results to that external data store. Just so that whenever we do the result, we can do everything locally, and we don't have to again go and do each. I guess it's the same, but it makes sense to me to kind of do it this way. So yeah, so the reduce and result data is going to land here. Okay, so that said, yeah, let's just go ahead and show that, or I think I've already created this in a prior run, so let's just maybe, okay. So here, for example, let's go ahead and list the data. Instead of creating, let's just go ahead and list. And actually, this would be better. So notice how we have on each one of these machines, we have a mount directory that each has, for example, 2 additional directories. So mount data, and this is empty. Yeah, this one is, so this is empty, but it exists, and this is also empty on node 105, and yeah, it exists, just because there's no error. So now let's go ahead and do the test job. So let's go ahead and go into our workflows directory that we talked about earlier. Let me just ls here. So we have 2 workflows here. We have a small workflow that's gonna let's just go ahead and look at it. So this workflow, for example, it's just for kind of testing, but it's gonna create 1,000 edges, random edges with a random world graph, and it's gonna cluster them with an algorithm that we talked about, the modern version of the MinHash, and it's gonna write the output to this sort of to this directory. Then yeah, the reduce path, we don't need to pay attention to these, but let's actually go here, because we're calling everything within this command. So it's gonna execute shell, and then it's gonna execute this program, stage map. So it's just gonna be a 1,000 edge node. It's a small graph, and compared to the amount of data, the billion edge graph that we want to show in this demo, and then it's going to map this phase right here. So this is what we already talked about, and it's going to do this for 10 times. So that means that we're going to multiply this by 10. That's 10,000. So we're going to cluster a 10,000 edge graph. So there are two ways of submitting the workflow. One way is you can do the remember the client that we installed up here. So you can use the client to submit the workflows, or you could do kubectl. You could use the kubectl interface. So for the first scenario, let's just go ahead and submit with the Argo client. So yeah, first let's go ahead and check that the YAML is correct. Okay, so no syntax errors, and let's go ahead and Argo submit. Okay, looks like the Argo is currently running, and let's see what's going on. Okay, get pods. So okay, so it's completed really fast. The mapping phase, it's already completed, and let's do this. Okay, so first, I guess what happened here is it's going to run the 10x because we specified we wanted a parallelism of 10, or what? Yeah, I don't 10 repetitions of the same job, 10 completion. So notice how it got scheduled. It seems like in around. Well, it got. This is the way the scheduler assigned each of the jobs to run, based on I guess whatever the default scheduling algorithm is. I'm not sure really what it is for Kubernetes. But anyhow, they got scheduled on all 3 nodes, worker nodes. So yeah, it seems like it ran to completion. Now let's go ahead and test these results. So we already did. So okay, so notice here before it was saying running, and now succeeded means that it ran all the workflow to completion with success, no errors encountered. And I don't know, maybe it ran pretty fast. So these completed within 4 seconds of creation, just because the program is fast. There were not very many edges. This is just kind of to test. So we already showed like how the pods got scheduled on each of the nodes that we have available. We showed like the parallelized or distributed sort of clustering technique. That's embarrassingly parallel. And let's go ahead and look at the data. So, okay, I'd rather do without the, like this. So here on node 101 on the local directory mount data, recall we showed it was empty a little while ago. We got all these map results. So in this case, these should be 10, one for each job. And yeah, that's correct. So pipe work count minus L. So we have 10 jobs that we ran. And remember that we said that we wanted to write the reduce files. So these are the partial results. The next sort of partial results is the reduced results, and then the last result is called the result. Okay, so we're writing that to that external NFS. Ooh, seems like it didn't get. Let's see, it should have gotten. Let me check that the workflow is correct really fast. So yeah, it seems like maybe the reduce files should actually be over here. If it doesn't show, I think we'll skip it for now. Maybe it's something I did right here. Let me see if there are any changes. Okay, looks like we have this external mount. What is this? Okay. Okay, so for now, I guess. Oh, I see what the error is. The IP is wrong. Let's go ahead and do that. Okay, so let's go ahead and do this again. Kget pods so wide. So notice how we don't have these pods here anymore, and the reason is that so these did complete, but they wrote somewhere else. Or yeah, let's try and do this once again. So this is kind of like the test, like a small graph clustering for testing purposes. So git pull. Okay, and then let's go ahead and submit that again. Kget pods so wide. And let me see if we can do watch kubectl. just so we can monitor it real time. Okay, so everything's completed. First the mapping, then the results. Here the reduces, and then the results. So this seems better now. I guess it's still trying to complete the previous run, and it just barely was able to complete it because of those changes. Okay, so now let's go ahead and do the same proof. First, let's go ahead and proof this. So now we're gonna have 20 just because we've ran this twice. That's why we have all these. Maybe I think even the reduce, since the reduce takes all of whatever map. So there should be a cleaning phase after the life cycle ends, but for now we're not going to worry about that. So that's the map data. Let's go ahead and see if we can look at the result data. There we go. So now we actually have the so we have 3 nodes. Recall that our Kubernetes cluster is 3 nodes, so each node is going to gather pretty much all of their it's going to combine all of their partial results into like a node result, so to speak. So these are still sort of like more larger aggregated results, and the final result, I'm actually writing it to a JSON, and the main reason is because I want to sort of so these, maybe to talk a little bit about the format. This format is actually binary format. It's just to make it like super efficient with no overhead and all of this good stuff. So this is binary encoding, all of this except for the result, and the reason for it being JSON is basically so that we can sort of create a dashboard and show like the results, how the data distribution got clustered and all of that good stuff. So yeah, and we'll look at this sort of later on. So that's the small test. We just clustered a 10,000 edge graph. Now let's go ahead and execute the billion edge graph. So first, let's go ahead and remove old files. And let's go ahead and ls just to make sure that's all clean again. Okay, looks good. And we're ready to execute the larger workflow. So again, we're just gonna check the syntax, and before I submit this, I want to make sure that this has the correct IP. Yeah, see here we're gonna have to modify this again. Okay. That was a small mistake right there. So git pull. Okay, now, whoops. Now we're ready to submit this super large. So okay, let's do the second. So instead of submitting with Argo submit, we can alternatively submit with kubectl client. Oh, this is workflow large, or yeah. Okay, so I'm just curious. I've never tested, but Argo list. Yeah, it seems like it also identifies it here. And get pods so wide, and let's monitor this like in real time. Okay, so it started. So here, I think we already talked about this, but we're generating a 16 edges per job, so to speak. And each of these jobs is getting scheduled on a different machine, whatever has enough resources available, because we're probably maxing out this environment, I'm pretty sure. But the code is pretty tight. It's sufficient. So so yeah, seems like it's working. and it's completing all of these tasks. They're going to be, so we said 16 million edges per job, and we're going to run 60 jobs. So, and you can hear that machine working right there. So I actually have this small server here, kind of like next to me, so you can hear that bad boy is working. Okay, so let's go ahead and just monitor here how. So it seems like it's completed in 1 minute. So we've just clustered a 1 billion edge graph within one minute. So that's pretty cool. And this is like an old server with not too many resources. But yeah, this is awesome actually. So, and I don't just say that because I wrote it. But anyhow, so this is like the large execution. Notice here, okay, what we mentioned, all of these edges, and we ran for 60 iterations, probably somewhere there. Here, 60 maps, and of course the reduce is going to be very simple. It's going to be the same. It's just three reduces and one result. So the complexity is going to be in this embarrassingly parallel thing right here. So here, this is actually important whenever you run distributed, like what I just ran. So you can control the maximum jobs executing at any given time. I guess if you have enough resources, you can just max out. But for a little better control over my old server right here, I just specified 10. And this right here, this parameter means, okay, how long do you want to keep these logs? So 100 seconds, just for now for me is fine, because if you have an error, you can, let's see if these are still there. Okay, get pods. Oh, okay, so we lost them already. But you can also do something like this, like k logs minus f. So you can look at the what's going on. Okay. All right. So that's this portion. Now let's just I guess for now I didn't really have enough time. Like I've done this demo before where we can create like an Elasticsearch database and use it with Kibana dashboard to kind of look at the frequency, or sorry, the distribution of the clustering technique, and see if it's good enough for your use case. So the use case, I guess for, okay, I'll talk about this. Let me just first prove it, just before we hop on to the next step. Let's prove that our that this is complete. So ideally here we want to have 60 completions. I don't know why we have 69. Yeah, we don't really care if we have 69, because since this is whenever we group by key, it'll just group to the same sort of it's the exact same result. So it's like saying 1 times 1 is equal 1, right? Or I don't know a better analogy, but essentially, if yeah, we don't really mind, so to speak. It's actually better. Like if a job failed at any given point in time, it's better to kind of try to redo the job, either on the same machine or on another machine. So actually, that would be interesting. Let's try and word count, like how many completions did we get on each machine. So for example, this machine did 24. Ideal or the exact, it should have done 20, for example, if it just ran once. So this other one got 21, and last one, 69 minus 24 minus 21 is, so this got 24 as well. So this talks, or maybe this, sorry, maybe this machine 102 has less resources or something happened on this machine, or I don't know. But it's just good to know. Maybe at least what I'm thinking happened here is 9 of the jobs failed, sort of at a partial point in their execution runtime, and maybe the scheduler said, okay, let's put this on another machine. But anyhow, we did get the results, so that's fine. And maybe this last thing right here, let's just test the reduce and result. And yeah, we have the reduce and result. So let's go ahead and SSH to this. Now let's talk about the next phase, or some use cases that you can follow up on the clustering, right? Why do you want to cluster? So let's SSH here. Okay, so notice here, these are the reduce files. Maybe if we can, it's just nonsense. If you look at the cat, it's just binary data. So let's see if we can, let's look at the weight. So how much each one of these weighs. So I think this is in what looks like it's bytes or something like that. Let's see. Oh, nice. So 64 megabytes each of these reduce files. So yeah, so it's not too heavy for like a billion edge clustering, right? And that's just because we're doing the metadata, so just storing the indices. And of course they're hashed and all of this, so we're just interested in like, yeah, in the sort of clustering piece. And let's see if we can analyze this. Maybe it's, let's see, VI Regal. Hopefully it's not too, yeah, it looks like it's, I shouldn't have done this. Maybe should have, anyhow. Okay, let's see. Alright, let's, oh, yeah, this is too large. Okay, let's just, hopefully the JSON did not, let's see. Yeah, it's too much. But yeah, this is the data that only makes sense with the visual sort of, visually, so to speak. So the next, so let me talk about the next sort of step, what to do after you cluster. So there are different things or different use cases that you can use for clustering. One is maybe just to identify, okay, maybe you have this large graph, right? Sometimes you might identify, so let's say that we did, as I mentioned earlier, I did not have enough time to kind of, maybe I'll show it as a follow-up video, but so the README, the last portion here is, so we have an Elasticsearch database. We create an index where we want to look at the bucket frequency. So how many edges are on each bucket, and what edges as well. And the reason we store the edges and not the nodes is because in case we need to create sort of like an induced subgraph sort of thing. So that's the main reasoning that I chose to store the edges. And also we also would like to analyze. Let's look at this. See, table or graph. So just for visual intuition at least. So sometimes we would also want to analyze like the data distribution. Maybe like maybe for example like in this type of distribution, the normal distribution, you might identify that we have sort of like larger principal components in the graph. And this is not too useful for like for some use cases, but it's useful for some others. So for example, as I mentioned, in this case, if your data distribution looks something like a normal distribution, or even something like something like this, this means that you have a large sort of principal, like a large graph that has all these connections. So I don't know. Let's just a quick analogy. So yeah, maybe no, without analogy. Let's just look at the math. So that would mean you have a super large graph, and then you have smaller sort of graphs laying around somewhere here. If you have this type of spike, if you have a more normal distribution, sort of like this, you maybe have things sort of like this. Maybe it's more uniformly distributed, and maybe small clusters isolated, sort of like all over this cluster space. Now, this is interesting to kind of just analyze the, well, for certain cases. So, for example, I guess, yeah, and there's another type of graph that it's more like the uniform distribution, which this is the one I'm actually interested in, and I'll talk about why. So where data gets more distributedly, evenly distributed. So in this type of analysis right here, I mean, you can identify, okay, this is a pretty large cluster, and maybe kind of look into the details of what this means. Maybe there's a popular pop song that's currently on the hit list, and here maybe there's some indie songs that maybe are not as popular or don't have as many views, or whatever type of analysis you want to consider. But for this case, I'm actually more interested in this type of distribution, and I'll talk about this. Let's look at this here. So the particular problem that I want to solve is something called the ANN. It's not artificial neural network, no. This means actually approximate nearest neighbor search. So what is this problem? What does this mean? So let's say that, and let's say that ideally, if you want to perform this approximate nearest neighbor search algorithm, ideally you want to have a uniform distribution. So something like this. Maybe you want all of the clusters to have, on average, or plus minus, but the same amount of edges on each. So something like 25 edges, maybe 30 here, maybe 12. I don't know, depending on your margins. But you can imagine, so almost all very close to like the they're uniform distribution. So maybe 24 here. And the idea is because in order to perform approximate nearest neighbor search, let's say that this is the graph that we've already clustered, and they're all, so recall here in this case we're going to have like uniform sort of clusters that are all the same size, and just you can imagine all of these having like edges, like smaller clusters right here. So this is a use case number one, and I'll talk about this. And then I have a second use case, which is called, I guess, yeah, well, let's just keep it at ANN. That's the fundamental reason for, at least in my in my area to want to cluster in this way. So whenever you do approximate nearest neighbor search, you usually have to do a full scan of so it's in big data. It's impossible. Let's say that you're working with genomic data. In order to perform ANN search, or actually just search in general, let's say that you have a super large data set that's the 1 billion data set that we just performed right here. If you want to find, let's say you have a new node or a new edge right here, and you want to identify, okay, what is this edge closest to, or where should I cluster this edge? So if you didn't do like an approximate solution, you would have to do a full scan right here. So you might imagine, I don't know, scanning 1 billion data points, and that's not an ideal solution for big data sort of thing. So big data, maybe this is probably a use case for like genomics or Google search and all of these types of large data sets that you may have. So that's why we actually choose to do ANN. So this means, okay, I'm not really interested in, I just want an approximate solution that's sort of within the ballpark. So let's say that we have this new data point, as we talked about earlier, and we're going to hash this data point. So let me do this. So we're going to hash this data point, and this hash is actually going to land on one of these buckets. So let's say that this particular data point hashed to this bucket. So that means you're actually saving all of this. You don't even need to scan all of it now. You can just skip all of these things and just perform nearest neighbor search on this bucket right here. So you can of course kind of play around with how sparse or how many buckets, k buckets, and different. I guess people call it different names. Sometimes it's called buckets. Sometimes it's called buckets. I don't know. I remember there being like many different names for the same concept, but yeah, essentially. So we're kind of, we can have as many buckets as we want. So in this case, like we had 1 billion edge nodes, 1 billion edges in a graph, and we I think for this particular case I chose 65,000 different buckets just because it made sense. So let's do a quick calculator here. So for example, we did what, 2 to the 24? Yeah, that's the 16 million edges times 60 iterations. That's the billion edges that we have, divided by 2 to the 16, I think is so we would have around about 15k edges per smaller graph, so to speak, per each one of these, where we need to perform our ANN. And there's also optimization, so you don't have to do a comparison operation between all of them, like a full similarity measure operation on all of these. There are certain ways where you can determine like a theta threshold, where let's say that let's say you take a small sample of 3. Okay, let's talk about this further down. Let's just finish this idea right here of like the ANN use case for clustering, right? For wanting this type of, or clustering this type of data. So I got a little, oh yeah. So we said each bucket is going to have around 15,000 edges. So each of these clusters. Now that we've selected a bucket or a cluster where this particular, it can be like a search query. It can be maybe it depends on the use case, but let's just say that you have a search query, you hash it, and then like the nearest searches are these, right? Or yeah, it can be recommendation systems, a lot of things. So let's go ahead and let's start a new sort of paint. right here, or yeah, refresh. So now that we've selected our bucket, we know it has around 15K entries, and we hashed our value, or our vector, so to speak, and then so we know it's somewhere similar to these. But let's say that we further want to sort of expand the problem, but we don't want 15,000. We only want, I don't know, the top 10,000, or even the top 10 or 20 nearest neighbors to this particular data point. So one thing you can do, if this is still too large of a number, I guess, yeah, or if you don't have enough time to kind of implement the next phase, you can leave this solution right here. It's 15,000 is not that much for like a billion edge graph. I mean, this is a good number. A good data reduction. Yeah, a good reduction of search space, so to speak.